Hello everyone, welcome to episode 9 of Warsaw.ai. So this event will be dedicated to natural language processing, and we have an honor and privilege to host 3 amazing speakers. Łukasz Kaiser from Google. He will tell us about Reformer, the efficient transformer. The next speaker will be Angeliki Lazaridou from DeepMind, and her lecture is titled Towards Multi-Agent Emergent Communication as a Building Block of Human-centric AI. And our third speaker is Tworek from OpenAI. He will tell us why language models are few-shot learners. This webinar is recorded, so the video will be later available on our YouTube channel. And I think we can start. So Łukasz, if you are ready, the floor or Zoom is yours, and you can start sharing your screen.
Hi, thank you very much. Can you hear me, first of all?
Yes, we can hear you. I will first stop sharing my screen. I guess that should be the first thing. And now, yes.
Okay.
Yes,
so while we're doing this, you know, guys, it's a strange year, right? So we're meeting on Zoom. So it's I feel like we're still kind of you know, figuring out how to do all of this. But I do feel like if you have questions, try to ask them as quickly as possible, because otherwise, yeah, they may get lost. I'll try to leave 5 minutes at the end too, but don't hesitate to interrupt. I feel the chat is sometimes a good way of just pinging that you want to ask, but if you just want to turn on your voice and ask, I think that may work as well. So with that said, can you see my screen? I hope.
Yes, we can see it now.
Okay, so I want to tell you about Reformer, which is about scaling transformer models and making them work on like normal people's resources, meaning not Google, DeepMind, or OpenAI, which is a bit ironic given the speakers today. But you know, I feel I'll tell you why I feel it's important also for the big companies to make things run for everyone. So you know, long time ago, so about 5 years ago in AI world, there were these things called RNNs. And people started figuring out that you could use them for NLP, and they basically solve all NLP tasks, right? The problem was that the RNNs were really slow, and like if you had longer sequences, like long sentences, the gradients did not propagate as well. And it's called long short-term memory unit, but it's not that long, this memory. It's really short-term, maybe 100 words, it's okay, if you tune it well, right? And then there came this model called Transformer, which solved this problem because the gradients hop in one step from any position to any other. So every word is attending to every other word. And I assume you kind of know what these things are, how attention works. So that's great. And transformers are amazing in the sense they can really solve your NLP problems. And especially if you download a pre-trained model, like a pre-trained BERT, and fine-tune it a little bit, then it will solve your problem. Now, the point is to really get great solutions for an NLP problem, you want a fairly large BERT. And BERT large, you know, on sequences of length 320, on a single 12 gig GPU, you can run one batch. But on 384, you cannot run at all. So that's a problem. And then you can do memorization and stuff, so you can improve this a little bit. But the question, and here is another example, GPT-3, which you'll hear everything more about in an hour or so. It can do wonderful few-shot learning, but it needs 170 billion parameters. So yeah, that might not exactly fit on your GPU. So can we, you know, the way it's looking is like in the near future, or actually already, it's impossible to even fine-tune state-of-the-art models without data center scale hard. And some people may try to tell you that's okay, like big companies like mine or OpenAI or DeepMind. But the truth is it's awful. Because what drives machine learning is really that you can do this at home, that you can improvise, innovate, find new things. If I needed to run every single experiment on the full data center, I would never be able to do meaningful research. So while we may try to sell you the best models, and they are great, right? So you should buy them. What we really want is transformers that run on a single GPU. And preferably, they should also run on entire books, not just one sentence or another. So you may say, well, okay, that's impossible. And what I'm here to tell you is, no, it's absolutely possible, and actually, it's kind of done. So here are the two challenges, right? There is memory efficiency and time complexity. So memory efficiency is like, how do we fit this huge thing into memory? And there are two parts to this. One is to use the accelerator memory efficiently, and there is something called RevNets. I'll tell you how this works, residual layers that help with that. And the other thing is, if you want to fit a GPT-3 into your machine, it will not fit into GPU, so you need to put it on the CPU RAM, or even on disk, but let's just say CPU RAM for now, and swap from there. And can you do this without being awfully slow? And the other part is the transformer, as I said, solved the gradients problem, but the cost of it is that the attention layer is O(n) squared, where n is your length. So if you put the whole book there, then it's O(1 million squared, and it will never run. So we need a solution to that, and I'll show you how to solve it with locality-sensitive hashing. Okay, so memory efficiency. Imagine you have 1 million tokens in your batch. So maybe this is one book that has 1 million words, or maybe it is 100,000 sentences, 10 words each. And you have the model in transformer of 512, then this tensor takes 2 gigabytes. Okay, 2 gigabytes can fit. And then you have 20 layers of that, or 12, and this takes 50 gigabytes. So yeah, 50 gigabytes is a bit too much, right? You won't fit it onto a GPU, even if you buy the newest one. But even if you do, what you really want is 100 layers, and then it will be 500 gigabytes, and that doesn't fit. And that's just activations, right? We're not even talking about the weights here. So how can we solve that problem? And the reason you need to store all of these tensors is that when you do backprop, you'll need these tensors to compute gradients, right? So what we're proposing is to use reversible layers, which can recompute the output from the input from the output. So how do reversible layers work? I assume you all know residual layers, which are just, you take a tensor X, so that would be what's here at the bottom, and you add a layer of X. Layer 1 would usually be attention, layer 2 would be feed forward. So you have F plus layer 1 of X, and then you add another, to all of that, you add layer 2 of X plus F of X. Okay. So that's the standard transformer. In a reversible network, it's different. You split the tensor into 2. So when you start, you actually start with 2 copies of X. So you're paying the price of 2X activation memory. And then to the 1, you compute layer 1 on the first part and add it to the second part. And that will be the new first part, as is on this picture. And then you compute layer 2 on this part you just added it to, and add it to the second. Now, why are you doing it like this? Because if you do it like this, when you have the 2 parts in the output, then you can, from this, compute the input running these layers again. And it's like just swapping signs in an equation, If you have X plus Y equals Z, then, Z minus Y equals X, right? So if you take this second part of the output and subtract layer 2, then obviously you'll get the first part. And then if you subtract layer 1 from the swap parts, you'll get back the input. So these layers are fully reversible in a very easy way, but they work very well. So what's the advantage of reversible layers? Okay, now you can have 4 gigabyte activations in every layer, but because there is no caching needed, you only use 4 gigs of memory. You allocate, deallocate, allocate, deallocate, and so on. 4 gigs because you need 2 times the activations, and actually you need the input and the output. So maybe you'll use 8 gigs, but that's much better than the 50. And do reversible layers work as well as residual in transformer? Yes. At least when you have like 6 or 12 layers. We haven't tested it with 100 layers yet, but we hope it will be good. If not, there may be some forgetting needed when you have more. Okay. So we have very efficient multi-layer blocks. Can we make single layers efficient? Like the feed-forward layers, they usually have DFF, which is bigger than the model. So the intermediate activations can be huge. But this is easy to cope with because you can chunk it. Chunk means if you have 1 million tokens, the feed-forward layers are pointwise. You just process it, slice it on the length, and process it, and that's it. How about attention layers? Well, attention layers can be large too, but you can slice it on the query dimension and process it one by one as well. So you can make it a little bit more loopy and save memory inside the layers as well. Okay, so that kind of solves the memory on accelerator problem. Now, how about time complexity? So all the feed-forward things are linear, right? They are O of length, where length is length time batch, and that's how it is, and that's okay. The problem is attention, right? It's QK transpose. This is L squared for length L. If you have 1 million tokens, that will be way too slow. So how to make it faster? You need to start thinking, what is attention actually doing? And what you want from attention is to pick a small subset of elements, right? It's supposed to be sparse. So how can you get, and the keys you want to pick for a given query are usually the nearest neighbors in vector space of the given query. So how do you pick nearest neighbors without computing the matrix of all distances? This has been known in computer science for a while, and it's called locality sensitive hashing. And there are many ways to do locality sensitive hashing, but here is one very simple way. So if you have these dots are your vectors in a space, and you want to compute nearest neighbors to each one in a fast way, here is what you can do. You draw a few lines in the space. So here we have 2 lines, and you will only compute the distance matrix among points that lie on the same side of the line. So the blue will only compute their distance matrix to the blue, the red to the red, the black to the black, the yellow to the yellow. So you see there is this blue point that will probably not find the right neighbor because it will be matched with this other blue point. But okay, so it's not perfect. It's a probabilistic algorithm, but it's much faster because instead of computing all by all, you compute 3 by 3, 4 by 4. So yeah, so that's a fast way of computing nearest neighbors. And now to use this efficiently on an accelerator, you need a little bit of tricks. So you have your sequence, and here we'll assume that queries and keys are the same. And you bucket it. So the colors are now which is your hash. You sort it by the bucket. And then now some buckets may be small, some buckets may be large. That's a problem for TPUs and GPUs. They really like things that have predefined memory size, so they can pre-allocate and so on. So what we do is we chunk them into blocks of a fixed length. This length is usually like about twice what you'd expect in expectation to be in a bucket. And then what we attend to is to the same hash within a bucket and to the previous one just in case it overflows. So this is a trick to make this work fast on the hardware. And as I said, well, LSH attention has this problem that, you may have this point that doesn't fit, like it's a probabilistic algorithm. You've chosen random lines, the point may be close to something else. The way to get better is to choose 2 other random lines and redo this. So this is the parameter we call n hashes, and you can, the more you do, the more accurate you will be in approximating the full attention, and these are results on ImageNet. So the bottom line, the dark one, is when you have full attention, and as you see with 2 hashes, you're not that good. With 4, you're better. With 8, you're getting close, and with 16, you're almost as good as full attention. And if you let it train longer, it actually gets there. Okay, so that's LSH attention, and it's actually much faster because it has this constant hash bucket size and only looks at that. So the longer your sequences, the more you gain in speed up versus full attention. So that's the reformer paper, and go read it if you want to learn more details. And I wanted to tell you a little bit about like newer work that we're doing to move this forward. So there's this GPT-3 thing. And if you wanted to run it on your computer, well, Reformer is very efficient, but you still need to, well, what we do care about here is generalization, first of all. And GPT-3 is just a transformer. So there are 2 questions. One is, can a transformer generalize better? And GPT-3 has problems with arithmetic, reversing words. So yeah, GPT-3, for example, cannot reverse the letters in a word. And we've seen in music transformer as well that relative positional embeddings give huge gains. So what we can improve is have better positional embeddings. And what we've also found is that adding RNNs, so RNNs are back, adding RNNs in the feed-forward layers helps a lot as well. And when you combine these 2 things, then you can get like generalization to lengths that are way beyond training lengths. So say you train on just to copy something or some simple task on length 32 and test on length 128. And the normal transformer will just yield you totally random results, while with these improvements, you'll get really good generalization. So these are the tricks to make this generalize better. And the other thing is like, can you train these big models at home? Can you train them with 1 GPU? And I don't mean you'll probably not train them on the whole web, right? I'd assume you'll take a pre-trained model from somewhere, but you may want to fine-tune this, right? And we are, the model has 700 gigabytes of memory, so it's not fitting into your GPU. You could quantize it, so maybe it would be 300 or 150. But even if it's at 120, if you try to swap it from CPU, it may be very slow. But then what you can do with Reformer, like you can have 1 sequence of length 1 million, but you can also have a large batch of short sequences. So when you have a large batch, then you can amortize the memory swapping cost by the computation cost on this large batch. Now that becomes interesting because instead of this thing that you have down there, that's a TPU pod, you can just run at home. And does this large batch amortization work? This is a screenshot from a TensorFlow profiler. So you see you have gaps here. These gaps are where when you're swapping memory. So you are like 20%, maybe 30% slower. But actually, you're quite efficient. You almost match the efficiency of training the sharded models while training on 1 GPU. So that's really nice. And other new work that I was working on with some colleagues from Warsaw actually is making this whole thing work with RL. And I think you will hear very soon about why it's really important to use RL in NLP. I believe RL fine-tuning is a source of a lot of future improvements in NLP. But if you look even at the basic RL algorithms, like you take PPO and try to make it work with large models and not so much data, then it doesn't work very well. And we've designed a new RL algorithm called Q-value-weighted regression. Well, maybe later if we share slides, there is a link here to it. That actually makes RL sample efficient while still being fairly stable. So we can match SAC, which is state-of-the-art on Mujoko, both at 100,000 and 1 million interactions. And we match Q-rainbow, which is a tuned rainbow for Atari at 100,000 interactions, and it gets better too. And the interesting part is it's the same hyperparameter. So in RL, there is a ton of tuning to make it sample efficient. And this algorithm in a wide range of hyperparameters just works quite well. So we're quite happy with that. Haven't applied it to NLP yet, but that's on the next to-do thing. So that's about the research. And now about the dirty part, because, deep learning papers are great. They show you the great things you can do, and you run a model and it does wonderfully. But then there is the dirty secret, which is like, how many tricks do you need in your code to make this stuff work? And Trax is a library for deep learning where we try to make clear what's actually in the code. So we try to make the tricks very readable and very clear, what was used where and how things trained. So what do you want from a deep learning library? Well, you want it to be nice and clean and so on, but you also want to run code fast, because if you're by any chance paying for your GPUs or TPUs, then it's important that the speed of the code translates into the money you pay, and you also want the code to run preemptible and on TPU, because buying a preemptible TPU is much cheaper than buying an on-demand GPU. So Trax runs, the same code runs on GPUs, TPUs, multi-host, single host, and it runs efficiently to very good efficiency. And we focused on making it really readable. And here is what I mean. So this is code for the Adam optimizer. On the left side, you see the Adam paper. It's a screenshot exactly cut out from the paper. This is the definition of Adam. Next is Adam in PyTorch. And, it's not too bad, but like, you need to know the magic names of things inside the state, and you need to set you need to get through this code. And the problem is, one day your deep learning model will have loss going up, and you will want to look inside the optimizer what's happening. So if you're thinking you won't need to read this code, you're wrong. At some point you will. And on the total right is the code of Adam in Keras. So if you're using Keras or TensorFlow, you will need to get through this code. So you will need to understand why we're using resource variables. And we're currently only using resource variables, but the non-resource one are there too because of historical reasons and compatibility. So there are good reasons for every line of this code, but they're often just to maintain compatibility. So with Trax, we decided, well, we don't need to maintain compatibility, so we can write Adam like this. It's kind of line by line from the paper, and what we use as interface is NumPy. So you would just say NumPy zeros, and it's really bag and get to code. And then we use layers that are combinators. So this is actually on the left the full code of the transformer, well, without the code of the decoder block and so on. But you just build layers with serial and layer norm if you want, and if not, you use NumPy functions, and you can. On the right is a full code to run a transformer to translate a sentence. Go to GitHub Trax and check it out if you want. What does it mean in practice? Well, it runs on, it's built on JAX, but it also runs on TF2. And it has a NumPy backend as well. So you can just run pure NumPy forward with no deep learning at all if you prefer. So you can get a safe model, run it on device, CPU, GPU, TPU. We maintain regression tests, so we daily train the models to check that they're still training. This is very important at Google because TensorFlow changes, JAX changes, everything changes, and you need to make sure the results you had a year ago are still there. It's also used in a Coursera course. If you want to learn it, you can check it out. And everything I talked to you about, like Reformer, the memory efficient trainer, special positional encodings, SRUs, which are fast RNN layers, the QWR layers. This is all on GitHub in Trax. If we share the slides, there are links here, so you can run it and check it out. So yeah, so that's it. And So I feel like the future is really promising. I believe we'll make transformers work not just in data centers, not just big models, but we'll make them runnable for everyone. We'll make them generalize better than they currently, just with better architectures and with bigger size. And hopefully everyone will be able to fine-tune them, which when you fine-tune, they work much better than when you just give prompts, right? So you'll be able to improve your own transformer the way you like. And I think the RL, this is kind of a segue to the next talk, the RL with NLP is probably the next big thing. So I believe RL will help NLP really be useful if you put it on top of large pre-trained language models. And with RL, the devil's in the details, right? You want a nice code and algorithms that are easier to tune, because otherwise you spend ages doing just that, debugging and tuning. So I recommend Trax for this reason, because we've put like a lot of effort to work with that. So that's it on my side. Questions, comments?
Okay, thank you, Łukasz, very much for a great talk. And it's great that you mentioned at the end that RL might be the next big thing in NLP, because in the next talk, Angeliki will be also talking about some applications of RL and NLP. But before that, let's just first ask some questions from our participants. So the first question, do you have some thoughts on why transformer decoder is not needed in machine translation problems and can be replaced by RNN decoder?
You know, RNNs work very well, right? They like the encoder is also not needed. You can translate with just an RNN. That were the first translation models. I think the main reason is that the sentences are short. Like RNNs work fairly well on short sequences. If you have 20 words in a sentence, it's fine. And in translation, like you need to attend the input sentence. That's a lot of attention, but you know, it's not that much. So yeah, yeah, that I think is important.
Okay, there are some more questions. The next one is, do you have some thoughts on limits of domain mismatch in multitask learning of transformers in context of a multilingual model of different tasks like translation, summarization?
I don't think I know much about it. I feel like if you have a large enough model, you can train on all tasks and it will be fine.
Mm-hmm.
But yeah,
okay.
I don't think I have much to say about it.
Okay. The next question is from Arthur. The entire NLP specialization on Coursera has exercises to be implemented in Trax. Do you think Trax is worth mastering by a casual data scientist? Do you think it might soon replace PyTorch as a standard library for deep learning?
Well, I'm not sure there is a. I mean, I'm not sure PyTorch is a standard. Like we still use TensorFlow a lot too, right? The advantage with Trax is that so at Google there is a problem running PyTorch on TPUs, right? There is an open source interface to PyTorch on TPUs, but I don't think it can run on like a TPU pod as efficiently as JAX. So I believe JAX is the future NLP library, and JAX doesn't give you a high level thing. It's just a NumPy interface to run on GPUs and TPUs. So I believe you should definitely master JAX, and Trax is written on top of JAX to give you a higher level interface. It's one of a few libraries. I think at DeepMind they use Haiku. I always believe it's good to know a few deep learning libraries. They're actually all very similar, and the differences are very educational. Like if you learn both, you will be in a much better state than if you learn just one. That said, I do also believe Trax is much simpler than PyTorch. As I've shown on the slide, you can read all of the code, right? I mean, I think it's 20 times less code than PyTorch. And that's thanks to JAX and TensorFlow to some extent. But yeah, I think it's a good place to start if you want to learn. And you're never a casual data scientist. It starts casual, and then 10 years later, you're not casual. So, yeah, plan for learning everything.
Okay, perfect. And the next question: what are your thoughts on the future of ideas behind RNN models? Do you see space for them to come back in the area of NLP, possibly in another incarnation?
Yes, absolutely. So as one of the slides says, I use now routinely RNN layers as the feed-forward block of transformer. And some people, like some of the new attention mechanism, like performers, they are actually RNNs in disguise, and they approximate, and then you can use them as attention. So I'm not sure exactly which part of the transformer they'll end up in, but I strongly believe they will end up being in there, except you need to make them fast. So to make them fast, you need to carefully choose which RNNs. LSTMs are just too slow, especially with long length. But for example, like SRUs, simple recurrent units, which was a not very well-known paper from also quite a while ago, they're really good and they're fast. So I use them a lot, and they improve transformers, like they improve generalization, they improve in speech recognition. Yeah, it's a very good idea to use them.
Okay, great, thank you. I think that was the last question from our participants. So thank you, Łukasz, once again.
Thank you very much.
Thank you. Let's now invite Angeliki. So I guess that, Łukasz, you should probably first stop sharing your slides. Okay, great. Angeliki, can you try to share your
Yes.
screen now?
Yes. Can you see the slides?
Yes, we can see your slides. Thank you.
Okay. Excellent. So, I don't need to do. You can see the slides, so I can start.
Yes, we can.
Okay.
Start. Yeah, go on.
Great. So, first of all, thanks a lot, Lukas, for this very interesting talk. Like it was very interesting to talk about efficiency together with performance. Anyway, I learned a lot, and thanks a lot for the organizers for inviting me. I was planning to talk about something more vague and obscure, but in the end, I will talk about something more concrete. And maybe I can start this talk by concluding that all we did was basically to try to take a pre-trained language model and combine it with RL through a re-ranking phase, that approach. And I'm going to explain what this all is. Before that, I want to say that this is a joint work with Anna Potapenko and Oliver Tillman, my excellent collaborators. And okay, we can, I guess, start going. So our goal in this work was to create an agent that can communicate with a human in natural language. And this is quite a broad and important goal for us in computational linguistics research. And in this work, we actually think that in order to be able to do that, we need to combine two strands of research that so far have been treated mostly separately. So our proposal is to combine a language model, think for example of GPT-2 or GPT-3, with multi-agent self-play. For example, think of AlphaGo, which became world champion in Go by playing against itself. So the idea is basically to combine language models and multi-agent self-play as a way to get the reward. And to be clear, in this work, I won't use neither GPT-2 nor AlphaGo, but rather simpler models that implement those very similar functionalities. Okay, so let's try to pick apart what I really mean by communicating in human language, and how can language models and multi-agent self-play come together for that. So I'd like to use John Austin's philosopher's phrase that says that people use words to try to make things in the world. So taking this statement, we see that use words to make things in the world really has two components. The things that we are trying to achieve, and the words that we choose to achieve that purpose. The things that we are trying to achieve are the what of communication, and this is like a really functional aspect of language. Now, the words are the how, just the how, the structural aspect of language, like the rules that form our grammar, basically. Now, the what part is the essence of communication. It is about what we intend to say or achieve when we communicate. And this is really a very goal-driven process. And an agent learning this aspect of the communication needs to be able to set goals and learn how to achieve them. And speaking about goals, I'm already hinting that reinforcement learning is a suitable paradigm for treating this what to say. On the other part of communication, we have the how part, and this is the surface realization of the intentions that we have, basically translating what we want into a sequence of words. This is not really goal-driven as what, because what we want to say is known. However, here we need, it's more like a passive mapping from an internal representation to the actual words, to the language. Now, for this how part, we think that it's very good to use language models because they have become really, really good at learning how words are pieced together. They can capture statistical properties of language, and they produce really natural-looking samples. At the same time, they are not really on their own that great for communication. So they're not that great at making things happen. No matter how natural-looking the language that they produce might be, they are still on their own not intentful or interactive. And I invite people also to read the recent paper by Emily Bender and Alexander Koller, where they have a very interesting and thought-provoking piece on discussing the interplay between language models and communicative intent, basically conveying that we have come really far with language models, but we are not quite there yet. Okay, so coming back into this division of how and what, the proposal here is to use language models, not to learn communication as a whole, but rather to learn just the how part. Now, to turn to the what part, the fact that we care about communication means that we are fundamentally in a multi-agent setting. And we want to use reinforcement learning because that is a good way to learn to achieve goals, which we want to pursue here. Now, multi-agent reinforcement learning is a very natural way, or like natural way, let's say, to do. It's a good way to do self-play, where we train a scaffolding agent that is going to produce rewards that could be used to train our primary learner. And in multi-agent reinforcement learning, the actions are things like moves on the chess or Go board, like moving up, down, left, or right. However, in our case, the actions are acts of communication. So our action space really consists of the space of utterances composed of the symbols that our agents have available for communication. So the agent learns to pick the symbols that maximize the reward rather than the symbols that frequently occur together, like, for example, in a language modeling task. As such, the use of symbols is really tied to the goal. So this is really a goal-driven way to produce utterances. Now, here it is important to realize that the communication symbols within this framework, as you can see, they don't have a priori semantics for the agents. They only get their meaning from the reward maximization process. I'm pausing here to say that this area of research of looking into how agents can learn to communicate and form emergent protocols is called emergent communication, and is also very often thought of as a scaffolding for language learning, natural language learning. I've recently co-authored a review article with Marco Baroni, which is, I have it here on the right, where we discuss recent advances, current challenges, but also like future steps for emergent communication. But coming back though to the using that for learning the what, we see that this paradigm on its own is not really enough to learn to communicate in natural language. We see that agents, they do learn to solve the tasks we give them, and they do learn to produce communication protocols, but these protocols, they don't resemble at all natural language, neither in the form nor in the type of properties that they have. For example, neither Zipf's law nor compositionality are observed in emergent languages. So no agent that we know of has been trained yet in this way that could also convincingly communicate with a human, like one way or another. So coming back to this, let's say, decomposition of communication and language, we will use self-play not to learn the whole thing end-to-end, but rather to learn the what of language. So basically, language models will be for the how, and reinforcement learning will be for the what. So how do we put these two things together? One way to do this is as follows. We are going to start with a language model, with a pre-trained language model, in fact, which is a general one and does not have an idea about the task that we want to use, the intentions that this model will need to have. And what we are going to do is that we are going to turn that general language model into a task conditional one by training it with the RL signal obtained from self-playing. And basically, relating it to what Lukas was saying, we want to take a language model and make it do useful things for us. And these useful things, they are, let's say, decided by the reward signal generated within this multi-agent self-play. Okay, to put it more formally, what this means is that we will take an unconditional probability distribution over text, like a language model, and we will turn it into a task conditional one by maximizing the reward received through the multi-agent self-play. Now, there are many ways that we could do that, and I'm actually going to talk a bit about some of these ways that we've actually experimented. Before we go to the models, to the models or to the ways that we've combined language models and reward, let me just give you a brief idea about the task that we looked into our paper. It's a simple task. It's based on the referential game, but when cast as a reinforcement learning environment. It requires two agents, the speaker and the listener, and the speaker is presented with the two images and is told which one is the target. And it then sends a message to the listener, which has to identify the target based on the speaker's message. Just to be clear here, this is a cooperative task, and it's to the interest of both agents to try to maximize the biggest possible outcome. Now, speaking about reinforcement learning, the state of the reinforcement learning environment is given by the two images and also the target indicator, like the fact that the target is the image to the right. The primary learner here is the speaker in this reinforcement learning loop, and the listener is there as a scaffolding agent whose function is to generate rewards that could allow the speaker to learn, to generate descriptions. Now, both of these agents can and are learned concurrently. And this is usually done also in the multi-agent communication literature, like both of these agents learning at the same time from scratch. What we want to do here is that we want to have a speaker that learns to generate a message like it's raining on the fire, a human language statement that correctly identifies the target. If it does that correctly, and if the listener then is correct at identifying the target, the both agents will going to receive a positive reward. Now, since we want the speaker to produce human language rather than any other type of gibberish, what we will do is that we will wire into the speaker a pre-trained language model that will act as a prior for communicating in natural language. We then will train it in such a way that it will learn the what using the rewards generated from the game, and it will use the language model's knowledge to represent the how. Now, coming back to the mathematical description of what we are doing, yes, the general language model will be a general captioning model that takes as input an image and generates a text. And the task conditional language model will be a discriminative captioning model that takes basically 2 images and a target, and it produces a text. So it needs to produce a discriminative caption, not just any caption. Note that we have now 2 types of conditionality here. We have the image conditioning that also a captioning model needs. But at the same time, we also have a task conditioning that a discriminative captioning model needs. We provide the first to the model because we have data for the captioning task, but the second type of conditioning is going to be inferred through the self-play. So we will induce basically this conditioning using the reward. Okay, now let me tell you a few things that we've tried and what we found. Now, first, how can we combine the rewards and the language model? So as Lukas said, like the first thing perhaps to do is to use the reward that is generated and fine-tune the model end-to-end, or do some multitask. But basically, both of these ways are changing all the weights of the model. Now, to start with, first of all, this, while conceptually simple, it's not always trivial, especially in cases like this where we need to extend the conditioning of the model. So we literally need to add something to the model, to the language model that was not there before, a connection that was not there, and fine-tune it for the task. So this can become really unstable. Now, in both cases, as we said, because we are doing fine-tuning, we will need to push gradients to the language model. So if that was a GPT-2, we would need to touch basically 1.5 parameters without accounting for the extra bits of parameters. Anyway, basically, yeah, it's a lot of parameters to change using just the reward. Finally, what we've noticed is that if we are not careful, pushing gradients from the reward through the language model that was pre-trained is going to cause catastrophic forgetting of language skills, leading to issues with fluency. Of course, this can be mitigated by introducing different kinds of regularizers for penalizing the model from diverging too much from a language model. But it's basically not easy. It's a headache. Like when we push rewards through the language model that has been pre-trained, it's very easy to make the model generate things that are not grammatical, they are not fluent. And overall, we observe basically that from a language generation point of view, combining language models with rewards creates, let's say, a set of problems, a set of language drifts. And I will present one here, a taxonomy, but I want first perhaps to explain why doing RL, why doing RL with language is not the same as doing RL with like any other type of environment with actions. And the main reason is that like in any type of environment, like let's say you are in some embodied environment, if your action is up, up, down, down, and you, for example, by accident, the RL tells you to repeat one action twice, up, up, even if this is a wrong action, it won't really make visually a difference. But in language, if our action space are the words, which is the case when we fine-tune on the word level, if the reward model tells us to repeat a word, this is going to look like really bad from the natural language perspective. So basically, when we use word level space to fine-tune our language models, many things can break really easily. The types of things that can break are the fluency, and this is what we call structural drift, is when the model is not grammatical. Other things that we've observed is the semantic drift. This is when the model is grammatical, but like starts referring to things in a completely different way. And finally, the third type of drift that we've observed is the pragmatic drift, where, for example, the agent says Jenny is sitting, And this is like accurately really describes the image itself, the target image, but the speaker and the listener, they have formed a convention that Jenny is sitting really means the pixels at the top in the center are white. And so while agents are able to co-adapt to each other and assume an interpretation for a natural language that is unconventional, this causes humans not being able to really understand the language produced by the models, despite the fact that it's fluent and grammatical and it has like all the nice, it's very natural looking. The good thing is that we can detect some of these drifts either with a pre-trained language model or in some other ways. The pragmatic drift is like very difficult though to detect, and because we need actually the human's interpretation of the message. So it's something to have in mind. Anyway, and at the very end, I would like to talk about like the most successful architecture we found. Conceptually, it's really simple. It's basically re-ranking samples from a pre-trained and frozen language model. So the whole story is going to work like this. The agent starts by sampling a bunch of captions from the target image from its model. And these captions, note that would all be more or less relevant to the target image. Now, it has to learn to select a caption that is likely to result in communicative success. And note that while all these captions are relevant to the target image, not all of them are going to be equally discriminative of the target, as the captioning model, the base model, hasn't really been trained for that particular task in mind. Now, this captioning model, the base model, will act as one of our baselines, and the question is whether we can actually do something better by accounting for the second image and for the reward that is going to get generated from the self-play. So what we are going to do here is we are going to introduce a re-ranking module. The re-ranking is going to make use of the samples and their scores under the captioning model, but the gradients that will come from the reinforcement learning loss, we use RL loss here. Sorry, the re-ranker it's going to get gradients only from the reinforcement learning loss, and we use reinforce here. And then what we do is that the final message is going to be sampled from this re-ranked distribution of captions. Now, mathematically, what we do here is to factorize the task conditional text probabilities using base rule. And the gray part is the pre-trained and fixed captioning model. And the red part is the estimated probability by the speaker that the listener will guess the correct image with a particular message. Now, this red part is where the task conditioning actually happens. And note that the reward model is never going to touch the language model. The reward is only going to affect this red part here. So basically what this means is that we are doing RL, but using as action space, not words, but rather samples from the language model. And this, we have a lower risk of catastrophic forgetting. Does it work? Yes, it works. We actually took our model and made it communicate with the human listener. I think the most important comparison is perhaps with the base language model, that is the structure under the gray. And we see that if we use this model and on top we use the reward, we can do much better than the base language model. So the reward has enough signal for us to re-rank and get something better out from the samples than the most probable sample given by the language model. That's it. Basically, that's what I had to talk about. Basically, one thing to take in mind is that it's possible to use reinforcement learning to make our language models do something useful for us. And perhaps instead of doing RL on the word level, maybe we can perhaps think of doing RL on the phrase level or on the sentence level, as we did here. That is something that perhaps can be more efficient because we don't need to train. We don't need to push gradients all the way through the model. That's it.
Okay, thank you very much, Angeliki. Let me check if there are some questions. We don't have questions on chat, but I will ask. I will ask one question actually, because working mostly in the transportation area and have to deal with autonomous vehicles, which potentially can also communicate with one another or with the road infrastructure. Do you think that similar methods can be potentially applied to just let the autonomous machines, autonomous vehicles, for example, to learn an efficient communication? I'm just curious because maybe it's not a straightforward application, and of course, in that case, probably we don't need a natural language model, but it can be maybe some other language which we just should be learned. But yeah, that's just an initial intuition based on maybe another some experience that autonomous vehicles are also very often trained using reinforcement learning as well. So I'm just curious whether you have been thinking about such potential applications, or maybe there might be some other applications as well.
So I mean, to some degree, I think you've answered the question in the sense that we can use communication. I mean, we can learn. We can have agents that are learning how to communicate in order to maximize, like in order to collectively, for example, solve a task better. Mm-hmm. I think one thing, I mean, and you don't need to have that in natural language. Of course, actually, natural language makes things perhaps more difficult because, like, it needs. So inferred communication, emergent communication might be better fit here. One thing that perhaps might be challenging is the fact that, like, with autonomous communication, with autonomous agents, most of the times each agent has their own reward function. Mm-hmm. So its agents are self-interested, but at the same time, they all need to achieve the best they can in the constraints of, like, all the other agents, which means that when we have emergent communication within self-interested agents, it's a bit more difficult than when we have emergent communication with cooperative agents. Mm-hmm. Just because we don't always know the reward function that every autonomous agent might be optimizing, so it's somewhat difficult. Yeah, like, and then the question is, can we have, for example, a centralized component that could regulate these autonomous agents? Yeah, but it's a very interesting question. At the same time, it's somewhat challenging, but, like, in an interesting way challenging.
Okay, yeah, that's really interesting, because I know that this is a very important and also interesting problem, open problem, in fact, in transportation area and autonomous vehicles area. Okay, but anyway, we have another question here. The question about the interpretation error, white pixels versus sitting girl. What method did you use to detect those problems?
Yeah, so, like, those problems are very difficult to detect, primarily because, so basically those problems happen when two agents achieve very high task performance. So, like, two agents together, you know, they're at 100%, and we take out one agent, we put the human, but this drops then, let's say, to 70%. We can only detect it from, like, seeing whether a human can understand the communication or not. And so, like, basically it's like we don't have an automatic way, just because you actually need the human interpretation. Like, you need to ask, how would the human interpret that? So either you need to have a human, or you need to have a model of how a human would interpret it. But basically, pragmatic drift is when two agents have co-adapted to a meaning that is very unconventional, and so a human cannot really interpret it. Mm-hmm. And we need a human in the loop, basically, for that. We can't really do it automatically very easily.
Okay, nice, thanks. So I have another question. So Łukasz, in his the last part of his lecture, mentioned that reinforcement learning might be one of the most interesting future research directions for NLP and enhancing NLP. So what's your perspective on that? Because you are already working on applications of RL in NLP. Can you also tell us about some other interesting research areas in this domain? If there are, but because maybe this is just a future for now.
I mean, like, okay, the clear thing here is dialogue. So like, is there a way to use pre-trained language models and make them do dialogue effectively?
Okay.
Because dialogue is one of the things where it's very, the reward is very clear. It's like, was the communication successful or not? Was the goal achieved? But then, like any task where it's easy to get a reward, and I guess like reinforcement learning for language tasks is perhaps, I would say, more exciting for tasks where we cannot where we can get, like, for example, summarization. Like, it's very difficult to write a very good summary, right? But it's easier to say whether that's a good summary or not. So I would say that I'm very excited for like the type of applications where even non-expert humans can give us good judgments, and where we cannot find expert humans to give us annotated data. So I think this is like the sweet spot of like exciting applications.
Okay. Perfect. Very nice. Thank you. And one more question, the last one. What would be your interpretation of better results at phrase level comparing to word level in the light of information theory, if any, of course?
Yeah, that's interesting. Like, I haven't really thought of that. I mean, like, somehow, I mean, yeah, I don't really have an answer to that. I'm not even sure if there is any. But I think the main reason why the sentence level results for us was better than the word level was because of the fact that we were restricting the search space of RL to something that we know we had somewhat good candidates for. So like, instead of having a search space of like I don't know how many words there are, and then time to the power of like the length. Yes, our search space was like 20 samples that we all knew were kind of okay. Yeah, I don't know about the information there. I would need to think about it.
Okay, anyway, it was a very good question. So thanks, Alexander.
Thank you. Yeah.
All right, I think that was the last question after this talk. So we can continue and we can invite Jerry. So thank you, Angeliki, once again.
Thank you very much, and yeah, looking forward for the next talk as well. Let me see how to start.
All right. Thank you. So Jerry, can you share your slides with us?
Yes, I'm here. Can you hear me for starters?
Yes, we can hear you.
Okay, let me try to show my slides. Can you see my slides?
Yes, we can see.
Okay, perfect. Thank you very much for inviting me, and welcome to everyone who decided to tune in to the Warsaw AI conference. It's a pleasure to be able to talk here, especially among such amazing other speakers. Today I have a chance to tell you about the project commonly referred to as GPT-3, and I will try to talk about it from a bit of a historical perspective, because I personally think like that the trends that this model represent is slightly more important and fundamental fact than even a single particular model we have today. To start this overview, like already in June 2017, the paper appeared that introduced all of us to the transformer architecture that already we all know like landed among the pantheon of the best and most successful building blocks for the neural networks we use today. One of the authors of that paper already had the chance to talk here today. And 1 year after that transformer paper appeared, OpenAI published the first paper now referred to as GPT-1, which trained a transformer of 180 16 million parameters on a data set of size of 1 billion tokens. A year later, in February 2019, we trained a model of size of 1.5 billion parameters called GPT-2 on a data set of size of 10 billion tokens. This year, we published results on another model of size of 175 billion parameters and of dataset size of 500 billion tokens. And to look back in the history, like how the time was then, which feels like a whole epoch in the past in terms of NLP and deep learning research. The things about the GPT paper, it used the transformer architecture, which was already well known, but it wasn't as established as it is today. It uses this technique of first generative pre-training on a big data set on a simple task of predicting the next word in a text that was downloaded somehow from the internet, and then supervised fine-tuning on a various set of tasks. And this paper reached the new heights of the performance on several benchmarks, academic benchmarks. And it is this moment, like together with a few other papers, is referred to as ImageNet moment for NLP, because as in ImageNet, people were generally downloading pre-trained models and then fine-tuning them for their tasks. And this moment, basically for NLP, also this technique was established that it was basically almost always better to download a pre-trained model that was trained on a very large data set and only then train on your own data set that is usually much smaller, rather than train from scratch. Then a year later, a GPT-2 paper came in, which used much larger model and a much larger data set, as I discussed. It used very few architectural changes compared to GPT-1 paper. It didn't even use any fine-tuning this time, and it reached again some breaking performance on a few academic benchmarks, even without any fine-tuning. But the most interesting thing about GPT-2 was that the samples generated by the models were kind of like pretty surprisingly high quality for the time and for what we expected from a model. The OpenAI decided to not open source the model straight away, but instead to do a more staged release for that particular case, to spend more time researching it, which generated quite a bit of controversy. Somewhere in the middle between a GPT-2 paper and a GPT-3 paper, there was published this totally amazing paper. If someone didn't read it, I highly recommend. I think it's one of the definitely more interesting works to read, called Scaling Loss for Neural Language Models. We already internally had quite a lot of experience training various transformers on a language modeling task, and we already saw a few regularities between these models, and we tried to look at them a bit more closely, and we discovered a lot of things that you really want to have. And it's very good that we live in a universe where all these things hold. Like one first fact, which is not even the most fundamental, but basically that the larger the models are in general that we use for training, the more sample efficient they are. With the same data set size, if you increase the model size, you can train a model to a much better your tests loss. And this is important in many ways, but particularly that actually the most compute efficient way to train your model to a particular performance you desire very often is to train a relatively large model for a relatively short time. And it turns out it can be more compute efficient. The problem you are kind of trading the test time compute, which for larger models is like sometimes higher, but there is a trade-off there that we now kind of know and we can analyze. Another thing is that actually the shape of the model, like the particular hyperparameters of a transformer, didn't matter almost as much as only the sheer size of the model within some reasonable bounds. But the most important result from the paper is that we basically could find out a very predictable rules of how if we want to invest a particular amount of computation budget for training a model, we knew what kind of performance we can expect, what model size to train to get the optimal results, and we kind of like discovered all those regular laws for training transformers on language modeling tasks that could guide us into training these models. we see a very regular scaling of what data set we use for training. And we see of a particular, anytime we increase a data set size of a given fraction, if we can spend as much compute to utilize this data set properly, then we can train a model to a particular amount of loss. The same thing you can see with like increasing the model size. And the most interesting thing is like that often the model training can be characterized by like the limiting factor. So if we can increase the data set size, we usually need to also increase like the number of parameters of the model and number of like computational resources we spend to optimize that model, to really like squeeze in all the performance to get like the scaling law that we see so regular on the left side, which is kind of also very, very interesting on a many philosophical questions. Like, you know, so far with all the models we've trained, we never saw this law break. This kind of relationship is holding for the biggest models we are training today. And there must be a moment where it breaks, because that kind of line at some point literally like crosses the moment where the model can predict the next word with 100% accuracy always, but like we don't know really where it breaks. And it's very interesting, like what that moment is exactly and what happens there. But most importantly, since we know all these relationships and we know all this kind of rules for transformers models, we could perform a lot of experiments on a smaller model sizes, new kind of they transfer into larger models. So that we didn't need to perform as much like experimentation on very large models. We could do them on small models, and then whenever we were ready and whenever we knew that this is the time, we could run a very large scaling model on a particularly big data set that we've collected to train the model that we know as GPT-3. And what GPT-3 did was as you already can like feel the theme here, with a larger model and a larger data set than GPT-2. It did very few architectural changes, almost nothing got changed versus GPT transformer. What happened that samples from a larger model can like maintain coherence for longer and are again like significantly higher quality than from GPT-2. But also we see something that is kind of new, which we call as meta learning capabilities in language models. There is this graph you can see here, which already you could see a few times before today, which shows it's a particular selected task to show this phenomenon, but it's pretty interesting to see what is happening here. What this graph shows is a performance on a particular task with amount of information you get in the context of a model before you query the model to do the task. So meta-learning capabilities of a model means the model can learn from a context it sees in a transformer, so from the text you give before. All GPT models are autoregressive models, single directional, so the following text is conditioned on a text before. And as you see, like if you give no information to the model, basically all models of all sizes perform pretty poorly. But if you start giving in the context some information from what do you expect from the model, like even if you give just a natural language prompt, which is just a statement in natural language, what do you want from the model, already the biggest model is kind of performing better. But the more information you add in the context, the more the bigger model quickly like catches up on what do you want from it. And then it can solve the task. Even if this is all done without any training to get the same as in GPT-2 paper. In GPT-3 paper, there is no fine tuning. There's only pre-trained model, and we analyze the performance of a pre-trained model. On this smaller graph on the right, you can see like this is aggregated performance after all the benchmarks we could. And really, if you read the paper, it's a pretty lengthy paper, and most of it is about like evaluation on various benchmarks, and basically as many like NLP benchmarks as there were in the literature the model was evaluated on. And the important thing we saw is that even like while the zero-shot performance is predictably increasing with scale, as we generally see that the larger models almost always do better, but with some additional information and context, the larger models do even better, and the gap is widening. And this is kind of like the whole interesting phenomenon which like GPT-3 taught us. And before this presentation today, I gathered a few samples from the model, especially for this talk today, so that I can show you what it means like meta learning in context. And the text in bold you see it is something that I have written myself, and the continuation is what the model has written. And it is all the time, this is the same model without any fine-tuning. I just put some information in the context, and then the rest is the text that model samples from it. As we can see, the model kind of what it knows. It knows, like, it gets the patterns from like what I write to it, and it learns to continue that pattern, which is, if you think about it for a second, this is some notion of intelligence somewhere in there. Like different people define intelligence like differently, but like continuing various patterns. Like if you've ever done an IQ test, usually you see some various shapes, and you need to continue patterns in some ways. And this is something kind of simpler in many ways, but something kind of in that way. I've shown the addition of some numbers and asked the model to like continue that, and not only it like added these two numbers, which is not an amazing task, but the whole thing is that it got my intention, it got what I wanted. Another thing, I've tried to ask the model if it knows capitals of some countries, and like the model seeing the whole Wikipedia, it is really good at memorization. So like it knows the facts, but the interesting thing is like it was enough for me to put a few countries and their capitals in there. And the model was able to like not only figure out what is the capital of Poland, but also give us a few other examples. And the last thing that I've tried is like if the model can translate from English into Polish language. And the model has seen very little languages that are not English. For sure, it has seen a lot of stuff, but the non-English language, it definitely like are very hard minority of the training set. But it was enough for the model to not only get what I wanted, but also provide a few other examples with the one caveat that it translates singular ear as like ears plural, but like the model is definitely not perfect. And if you even with this kind of things, I had to try to write prompts a few times to get what I needed in the end. This is kind of like the whole aspect that the model generally most of the time gets almost what you want, but to really get what you want, you sometimes have to rephrase a prompt a few times to really get the behavior that you kind of are trying to get to. And like one particular showcase of the skills of the model that's pretty telling, that I like to show to people, is that the model learned to use words it has never seen before in new sentences and invent sentences with these words. Like if we prompt the model this time, the non-bold text is the prompt with a prompt of the type to do a fardoodle means to jump up and down really fast. An example of a sentence that uses the word fardoodle is, and then we ask the model to write something. One day when I was playing tag with my little sister, she got really excited and she started doing these crazy fardoodles, which shows not only some amount of creativity, but clearly like understanding the concepts that are there and knowing how to use these words effectively. A pretty interesting capability of that model and a test of it, because it's very hard to quantify what does quality of samples of a model mean. There aren't really any good way to quantify it these days. But the one particular test we did, we gathered a data set from a news website of titles and news articles. They were particularly short articles, which is actually very important here. And then we asked the model for the same headline to generate article as well. And then we did a blind test on a group of 80 humans if they could detect which prompt was written by the model and which was written by like human editors. And we can clearly see that together with increasing the model size, this detection probability gets closer and closer to the random chance. For the bigger model, like the probability was around 52%, which was the most interesting, because like we are often afraid that the models that can generate pretty convincing, pretty good text can be used for some misinformation campaign or used to spam internet a lot. And this is definitely something that is getting more and more into the realm of reality these days. So we need to think about how do we want to handle that and how to develop countermeasures for these things. But as the model does a lot of things, there are also a lot of things it can't do, or a lot of things that they are not great. So like the from GPT-2 paper to GPT-3 paper, like a lot of time has passed, and people did a lot of amazing works. So like while this is a single model that is not fine-tuned in any way and can perform pretty well on most of the benchmarks, except for like really a small amount of exceptions, it doesn't really get like the best results ever of all the models ever published on many data sets. It is somewhere competitively, but not at the top. But more interestingly, like the short samples from the model are pretty good, but generally the longer they get, at some point they start losing coherence, they start repeating themselves. The longer the samples get, you can see that even though each sentence kind of makes sense in isolation, like the model kind of loses point somewhere, and like starts basically like spitting up text without that much thought behind it. And the model is mostly challenged about things like common sense physics, like if you put the ice into the fridge, will it melt? And often things like logical reasoning, like a grade school math or like textual entitlement. And then from a perspective of using it practically in any way, because it's models at least like of that can be quite general in terms of how you interact with them can start getting useful. But there's a question, like this model is trained on a data generated by humans, the data found on the internet, and that data exhibits all the biases and like faults we have as a human race, as people. But we often don't want the models to like be able to repeat that and do at scale all the things that we are not very proud of. So the question is, how can we fix our models to be better and know better? If you want to train your GPT-3, and if you want to train your big language models, like how do you do that? Like there are two basically important aspects of it. It's like one thing, you need to get a data set. Two, you need to get a big cluster of computers, of course. So to get a data set, this is often like the pretty hard part for it. But we are kind of lucky that we have the common crawl data set, which is publicly available for everyone, and it's a very big data set of really huge amounts of data downloaded from the internet. The only question is that it has a tendency to be slightly lower quality. So to train GPT-3, what happened? First, we had like this few data sets which we know were kind of higher quality, although much smaller, like web text, which is like a data set scraped from outbound links from GitHub with some amount of karma, which is some predictor of quality. We had books data sets which are books basically, and there's Wikipedia, which we know is pretty high quality. We basically filtered the common crawl data set, which is huge, to the data that was the most similar to other data sets that we know are good and are high quality. Basically, there was a train classifier that tried to classify documents for common crawl and for the rest, and we filtered out for the documents that are the most similar. And still, the common crawl was slightly undersampled in the whole training, while the higher quality data sets were upsampled, which basically, like in tests on smaller models, seem to improve the quality of the models on evals a bit. And the other thing is how to train the GPT-3 on a lot of hardware. And I really wanted to talk here a bit more about it. This is really an exciting slide, but unfortunately, as long as these things are not published, I'm kind of not allowed to talk about those things in a lot of detail. I'll try to like say what I can. Like one important thing is that GPT-2 was trained on a TPU pod. But once we finished the GPT-2 work and we knew our scaling ambitions still grew higher and higher, we knew we kind of will outgrow a single one at some point. And at that point, we knew we need to develop like technology ourselves, how to like scale training from one machine to multiple machines. So these days we have this technology. And we basically trained the model on like a lot of NVIDIA V100 GPUs with very fast interconnects. And the training technology is like, it's nothing groundbreaking. It's nothing very different from what you see in other leading research labs. So if you read a GPy paper from Google, like Zero paper from Microsoft or Megatron paper from NVIDIA, you basically will have all the same ideas that we do internally to train these big models. And the only like remaining part is like implementing the system pretty reliably and making sure it works well. To give the gist of it and a short version of it, there are 3 different axes of parallelism of how we can like split transformer into multiple machines that works well. The simplest one, which works almost always for any deep learning you do, is data parallelism, which means basically you split your batch for 2. You do the forward and backward pass in multiple copies of your model separately, and then synchronize gradients at the end to make sure that each models do the same step, and this just works. Another aspect is like model parallelism, which means you can shard each matrix multiplication in your model across 1 dimension, split this matrix into 2 pieces, again do the right all reduces before and after that, and then it works well. And the last kind of amount of parallelism is model pipelining, which basically you can say it quickly as you take different layers of transformers and put it on different machines. Like the first transformer block you put into one machine, and the second transformer block you put in a second machine, and then the first machine does like the forward pass first, then the second machine does forward pass second, and then you need to come back as the second machine does the backward pass, and then the first machine does the backward pass. You basically like split your model against like the 3rd dimension, and in that way you ease the burden on each individual machine, and then that way you can like scale your models even if they don't fit in the memory of a particular single GPU of a particular single machine. One thing that I want to add at the end, if there is still some time, is like I'm really happy that all the speakers today from before me like mentioned how they think RL is a big thing in NLP, because I think the same. And I would really like to highlight like one work which we did at OpenAI as well with kind of the models from GPT-3, although they with slightly smaller models, is that we trained them with RL to summarize articles. And this is a very interesting thing, because like we train these generative models to predict the next word in a sentence. And this is not an objective directly that optimizes sampling. This is objective that optimizes like sampling one word. But the models are good enough that if you sample like multiple words in succession, they don't drift too far, and those samples most of the time make sense. But RL is something that directly optimizes the quality of samples of your models, and this allows you to train what you want in the end, at least for some use cases. But then very often the problem is like where do you take your reward from? How do you wanna do the reward? So there was a team at OpenAI who decided like the only like ultimate judge of the model performance are humans, and so they collected a lot of like comparative scores of pairs of reviews from the internet to like so that humans can decide which summary is better and which summary is worse for a particular article. Then they trained a reward model for that for these rankings, because like as much as you would like the humans to be able to like go inside your training loop and basically like score the samples from the model as they are sampled, it's not very efficient and it won't work. But if you take somewhat like the knowledge from humans who rank a lot of articles, and if you can like bake it into a model, and if the model is good enough in a supervised way to represent those rankings, then you can use this model as a reward for your reinforcement learning to score the samples, and that can make your model better. And as we've seen before, the model just pre-trained model like has some performance on writing summaries, but they are often not good. And what we've seen very often is that the model can like make up facts that are not there in the text at all, or generally do things that humans don't consider good reviews. We tried in a supervised way to fine-tune those models, but the performance were not that great. But if we were able to use RL with human feedback used for training the reward models, it seemed that the performance of those summaries suddenly become much better and totally outperformed any gains we've seen from scale or supervised fine-tuning. So to summarize my talk today, like one most important like fact about models and about AI research is that even if we don't manage to create any new science as a research community, the models will get better every year, just to the fact we'll have faster computers and we'll be able to collect larger data sets. But the research into scaling models have like two important sides. On one side is a practical research, practical side, where if you are an applied scientist or like someone working in a business and you want to train your model, you can like look through research work that looked into scaling, and you can decide without performing a lot of costly experiments, what scale do you want, what data set do you need to collect, and all those things are kind of we see are kind of governed by some laws, and because of that you can guide how to allocate resources in your business, and other people don't need to do the same work because they kind of already know what's out there. And the other thing is a theoretical aspect, is that we as a researchers probably should like try to focus on various problems that the scale can solve by itself, because we know that in a few years, as the machines get cheaper and cheaper, some of the problems that we have today probably will just disappear, and we've already seen that trend happening all the time throughout like the whole history of AI research. But as better and better AI models like are becoming a reality, they also are creating a set of risks and threats which we as a research community must face and address somehow. One is of AI alignment, which means like, will the AI be doing what we actually want it to do? The other one is AI misuse, like which means that people may be using the technology to spread misinformation or in other ways against other humans, which we don't like, and how do we can prevent that? And something very relevant already today, and something that is already very close to us, how we can prevent the models from perpetuating biases and stereotypes that can actively harm someone. So thank you very much for listening, but that's what I wanted to share today.
Okay, thank you very much, Jerry, for a great talk. Are there any questions to Jerry or Jarosław? There is one question. Ilya Sutskever tweeted today, it can be hard to tell where memorization ends and generalization begins. My hope was that memorization generalization dichotomy might be simply false, not only from deep learning point of view, but also from neuroscientific point of view. What are your thoughts on the topic of generalization memorization?
Yeah, it's a very interesting topic. It's a topic kind of almost as old as machine learning. Like in the beginning of machine learning, we know that if we have a model that just memorizes all the samples from a training set and doesn't do much, it doesn't have an inductive bias. It doesn't generalize, and it does nothing. So any model kind of that can have some reasonable performance on any sample it hasn't seen in training is already doing some amount of generalization. But like one thing that is pretty challenging is that as the models, like we train them on bigger and bigger data sets, is those data sets are almost surely are getting contaminated with our benchmarks in some way, which we measure their performance, which in one way this relates to. Like we want to evaluate our models, but if the model has seen some of the benchmark problems, it's kind of it gets slightly less interesting, and the benchmarks lose their capabilities. But the one of the most interesting aspects is that if we look at humans as how we evolved as a species, like we evolved, like all the initial like things that shaped humans, we evolved for living in a jungle. And we hunted, we gathered food, we at some moment we even discovered fire, and that was amazing. But the times have changed, and now we live in concrete, we type on computers, we talk over long distances on a cable, and whatever this process that shaped human was, it was like good enough to adapt to it, and without minus a few like so-called diseases of civilization, we are doing pretty well in this new setting, and we are able to like generalize. And there's like one thing is like the model, whether the model generalized from a training set to test set, but there's always like this bit of an extra thing. Can the model generalize on something like very different from what it was trained, and will the model be able to still like solve these problems? And we in a few domains, like especially like when training RL models, we see sometimes things like that. But this is still a very open area of research. But like at some point, our models will really have to learn to generalize. and we will have to like find some ways to know whether on something like very different from what they were trained on, they can still perform. And especially like skills like meta learning and figuring stuff as the model like kind of goes are the most paramount to reaching that kind of skills at some point.
Okay, thank you very much for this answer. The next question: where do you see the most exciting applications of models like GPT-3?
Yes, so like one of the most exciting things, like the models can generate a lot of pretty good samples, but they are not always good. They are not guaranteed good. So I think like a lot of like creative fiction writing, where people write books, but still like the model gets edited, or like the human can select what samples they like or they don't like to include their books. That can be like really shortened, and basically like these days can be almost miraculously happen like in a time that it would never get done before. The models are a very good like kind of creativity enhancer, because like you can sample from a model a lot of samples, and then people creativity kind of works slowly, and people don't come up with new ideas that quickly. But you can generate a lot of samples from the models, and they can do a lot of crazy stuff there, because each one of them is random and different. And then it can like boost your own creativity, and you can get those ideas and sometimes somehow make it into something better. But another thing is that because the model kind of meta learns, I think it can become like a pretty useful like a prototyping tool, or something that you can do something very quickly. Because like we know, and it's a fact, that fine-tuning will and is beating meta learning. But the meta learning is fast, and you don't need to do anything to get it. So you can like literally experiment for the 10 minutes with a model, like writing a prompt, and then maybe you can hook it to some like application GUI designer or something, and then maybe you can create an app and a minimum viable product in like 2 days, which would previously take a month. And then you can gather some initial interest in your product, and then if it kind of catches on, you can like improve the process and make it better. So I think a lot of these things kind of already can be like a really good things for the model. But I think in the end, like, people have a lot of creativity, and people can try a lot of stuff for themselves, and maybe something else totally will also stick.
Okay, great, thanks. One more question: given current state of the art, how would you go about training similarly good language models of low resource languages? To have a model of English is nice, but how about Silesian, for example?
Yes. So like one thing that I think is pretty important is that when you train on a large data set, even if the most of the data set is not relevant for you, there's almost always some kind of positive transfer between those things. So I think like it's if you train on a data set that is in large part English, but it's in some other language only a fraction, it's already, the model will perform much better than if you train only on this language. You have much smaller data set. So definitely a language model will be highly limited by the amount of data that you have in a target language, and maybe there needs to be like some experiments held, like what is exactly the ideal ratio of these languages, and how to like whether do you want to first train on English and then fine tune another language, or do you want to train them jointly. But I think like there's a lot of time where other data helps, and I probably like, even if you put into the model like other similar languages from like a similar group or something like that, a lot of transfer that can happen. And I think this will ultimately boost like the performance of your model. But what is the like at the ultimate, the maximum top you can get from like the data you have? It's like a very, very open question. But just probably because of differences in data sets and how these things work, it's very likely that the English language models will like still always perform better, because just more data equals better models in the end.
Okay, perfect, great. I will ask one more question, because Łukasz told us about memory efficient models, and I believe that in the future we might want to have models of a similar accuracy, but models that can be run on smaller machines, or using smaller number of virtual machines, for example. So how do you think that it might be possible in the future to build models, language models of a similar accuracy and performance, but with a lower number of parameters? Or does the scaling law, which you mentioned about, prevents us from doing or achieving something like that?
No, that's the whole good thing about the scaling law. Scaling law basically says only things about like this particular architecture and this particular hyperparameters up to what we don't change, and this particular kind of problem, which is the whole helpful thing. And if you look at the OpenAI website, there is like an article about like how the research progresses, and basically like they analyzed a few different problem domains. And they saw that there was a trend that basically just due to algorithmic innovation and like people figuring out better like optimization algorithms, better architectures, the cost of training models to the same performance as before basically lowers by half every 16 months. And what the scaling law says is that for this particular like model, this particular algorithm, this hyperparams, this behaves like that. But when you change something and it actually improves things, the scaling law, like it's hard to say if the steepness, maybe even steepness can change, but for sure that they can be parallel shift to like to a different level. And this is kind of a lot of things what AI research is about, basically like making those things like cheaper and cheaper as the time progresses. And this is happening. This is what we are doing since 2012 kind of, and this is still happening these days. And all the research into making more efficient models and things like that is doing like that. What the scaling law says is that currently with what we know, this looks like that. And we hope it will be improving only in the future.
Okay, and can you maybe also tell us a bit about the future plans for developing this area further? So, for example, are there any plans for building training GPT-4, for example, or there might be totally different approaches on the way?
Yeah, so like I can't really confirm or deny here, but they don't like us talking about research that is not public in any way. But like I think it would be pretty weird if there was no any work like on continuing this research direction, and there surely will be some new ideas in one way or another. But I think that's everything I can tell about this.
That's fine. So maybe one last question if you still have time. Coming back to this scaling law and efficiency of training models, do you think that there might be some theoretical results, or maybe there are already some theoretical results showing what's the, for example, lower bound for the number of parameters in order to achieve comparable performance to GPT-3 or similar models?
Yeah, so like one thing that the scaling law doesn't really like say is that what can you do with like with a model of given parameters if you like still put like data in and compute in. But the problematic part in here is that if you are in a, like, let's call it infinite data regime, right? Let's say your data set is literally infinite and you can generate as much data as you want, and you have a model of a particular size and you train it. At some point it starts getting like improving very, very slowly, and that's kind of the whole thing. Maybe we need a way to improve it better. Maybe it gets into some kind of optimization plateau, or maybe it just can't. But my personal hypothesis is that not just it can't become better, but just our optimization algorithms cannot optimize it better. It's just the gradient, the local improvement cannot redirect it to become any better. And because of that, like whatever that limit is, it's like you can't actually say, because the model can improve for a very long time, but the improvements will be so small. There's no real actual like empirical limit for that. The whole thing is that the small models like become very, very slow in training at some point, which makes it like totally impossible, like with current technology and with current science, to train them to like the same performance as the big models, because like I said before, the big models are just super sample efficient. They just train very quickly, even though they are kind of like expensive to run. And that's like the whole trick about this model size, is that at some point it's kind of cheaper to train bigger model, because the smaller model will train very, very slowly.
Mm-hmm. Okay, thank you very much, Jerry. It was really interesting, and thanks for answering all the questions. So yeah, that was our last talk for today. I don't see more questions at the moment. So yeah, unfortunately we can't have after party this time, but the Q&A session was a bit longer. So just before the end, I will share a link to a short survey where you can give us your feedback regarding this event. And let me just share the last slides. That's just ending. I'm not sure if you can see my screen now. So yeah, first of all, thank you all for attending this event. I would like to thank the speakers for giving us really great lectures. So I believe that we really learned a lot, and hopefully the videos will be available soon, so you can also watch it later. If you'd like to stay in touch with us, feel free to join our Facebook groups, Google groups for mailing list, and follow our YouTube channel, or just send us a feedback by email. The next episode will probably happen next year in January, so we'll announce the date of this event in a couple of weeks. And that's all for today. So thank you once again for attention. Right now I will just stop sharing my slides and I will stop recording.